if it is fine or not. Share. Can you please confirm if you can see my screen?
Yeah. It's not visible, ma'am.
Could you see?
No, it is not visible. Anil sir,
Ma'am, it's not visible.
not visible. And have you made
Yes, ma'am.
madam as a
Access is given, madam.
Access already given, ma'am. You can use share option. There is
Which
an
option?
option here. Click on share and you can.
on the top right, ma'am? There will be option share.
Yeah, I'm doing that. Share this window.
Otherwise, share entire screen, madam. Entire window or screen. Ma'am, after clicking on share option, you will get screen and window. You
Yeah,
can
I'm
choose
just
screen, ma'am. Screen.
yeah. Share screen. I have done that. Share the screen. I have selected share screen. Could you see or no?
No, ma'am. No.
Okay, then let me
Not,
just.
not visible. Ma'am, you share to someone else, ma'am.
I've been trying. Just a minute. Let me try to log in with another machine. Please give me a few minutes.
Okay, ma'am.
Yes, ma'am. Hello, ma'am.
Yeah, I'm sorry. I'm just logging into the other machine. Just give me 2 minutes.
Okay, okay, ma'am. Okay.
Okay, thank you.
Ma'am, shall I share the link once again to your mail and WhatsApp, ma'am?
Can you open the presentation? What is the presentation?
Yes, ma'am, you can present now.
Yeah. Just a minute. I'm opening the presentation. Wait. Browser. I'm sorry for this delay. Where is the browser?
Okay, no problem, ma'am.
It's not recognizing. It's not recognizing.
Can you add them to them?
Yeah. Try, please try. Did you see if it is recognizing?
Ma'am, or can you share your PPT, ma'am, so that we will operate from our side?
Yeah, I can do that right away.
Yes, ma'am.
Yeah.
Can we hear it? Sharing a screen?
No, no, ma'am. Better you can share to Ghost, ma'am. They will share it. No problem.
I already have shared the presentation by email to madam. How can we do that? Share. Is it sharing or no? I have shared the presentation. If you can just share it, I can start the talk.
You shared to me, ma'am, to my mail ID?
Yes, madam, I have shared with you. Yeah.
Okay, okay.
Yes, ma'am. It is visible, ma'am.
Now it is shared, ma'am, from our side.
Yeah. Yeah. Shared. It is now. It is visible, ma'am. Okay, you carry on.
Before that, Shanmati, ma'am, please you proceed. Please
Yes,
introduce and
ma'am.
list all the participants.
Yes, ma'am. Good evening, ma'am. Good evening to all. It is my pleasure to introduce today's resource person, Paidi Ganga, ma'am. She is currently working as an associate professor in the Department of Electrical Engineering and Computer Science from Indian Institute of Science, Education and Research, Bhopal. Her primary research interests include analog mixed signal design with different semiconductor technologies for various applications. Other research interests include device modeling and devices. She completed PhD in 2014 from University of Porto, Faculty of Engineering, Porto, Portugal. After that, she worked as a postdoctoral fellow for almost an year in CENIMAT, Lisbon, where she was a part of various European Union projects towards the implementation of smart electronic systems using flexible electronics. Then she worked as an assistant professor and at IIIT Delhi and IIT Goa and joined IASCR Bhopal now. Her research work resulted in more than 60 scientific papers in international journals and conferences. She is currently IEEE senior member and she has been awarded an SERP Power Fellowship Weiser Grant for Indo-German Science, Technology and Corporation. Further, she has successfully completed 2 research-sponsored projects and 1 industrial consultancy project. Her ongoing projects includes MOE Starts, Wiser, India-Portugal bilateral project and consultancy projects from industries. She has shared SCDTE Flex Center webinar and gave various invited talks. Thank you, ma'am. Please continue this session.
Hello, ma'am.
Hello.
Ma'am.
Yeah. Can you see my screen now?
Yes.
Oh,
But
okay.
yeah, now it is visible, ma'am.
Okay, great. Just a minute. I'm very sorry for this technical glitch and the delay in this talk.
Ma'am,
Yeah,
PPT is not clear, ma'am.
can you
Oh,
hear?
now it's now, yeah, now it's
Okay,
okay. Now it's okay.
finally. Yeah, I'm very sorry for this technical glitch and the delay. And thank you very much to the madam and all the uh, organizing committee for this opportunity. Thanks for the very nice introduction as well. And I welcome all the participants to this talk. So this talk is about low power oscillators for IoT applications. The outline of the talk is as follows. First, I just would like to give a very brief introduction about ISA Bhopal, where I'm currently working, and the my research lab facilities and funded projects and some opportunities I have for researchers. After that, I'll enter into the technical details of these oscillators for IoT applications, in which we are going to see the conventional designs with CMOS technologies, as well as designs with emerging
நம்ம கம்ப்யூட்டர்ல தான் இப்படி வருதா? ஸ்கிரீன் ஏதோ மாதிரி இருக்கு.
Hello. And you can also see designs.
Ma'am, it is okay, ma'am. Carry on.
Yeah, designs with emerging semiconductor technologies. So coming to the institute where I'm working, it is the Indian Institute of Science Research Education, Science and Research Education, Bhopal. So we are almost 160 faculty with 2,500 students. We have, typically ISAs are mainly known for sciences, but ISA Bhopal is only the ISA which is having engineering streams. We have 3 streams: electrical engineering and computer science, chemical engineering and data engineering science. We have academic programs like BSMS, PhD, and BTech MTech. Soon we are going to convert this BSMS into BTech MTech. You can also visit our department website. The link is being given here. Coming to the research areas in our department, analog mixed signal circuit design, flexible electronics, robotics controls, and in addition, there are various other domains also. You can refer to our website for more details. You can see a few pictures about our campus, academic area, lecture halls, and hostels, and so on. We have state-of-the-art research facilities for sciences as well as engineering. And coming to my lab, you can just visit my website to check what research facilities we have. Basically, my lab is meant for custom IC design flow with different semiconductor technologies. We deal with flexible electronics as well as electronics for harsh environments, say for example, space applications and automation and so on. We have a lot of international collaborations with Fraunhofer Research Lab, Germany, and Unilever Research Lab, Portugal, Pragmatic, UK, and we do have collaborations with industries like Dipix, USA. Various projects that are undergoing on includes SERB projects and MOE stars, consultancy projects, and bilateral projects between India, Germany, and so on, almost with 3.6 crores funding. I'm looking for motivated PhD student, and if somebody is willing to do their master thesis here, they are welcome. I'm looking for at least 1 year duration. Yeah. Now coming to the technical details of this oscillators for IoT applications. First of all, what is an oscillator? We can have a couple of definitions for this oscillator. One definition is an amplifier with infinite gain. But this is not the best way to design an amplifier. Typically, if the amplifier is not having good phase margin, say about 60 degrees, then it tend to oscillate. There we don't have much control. So the other way, how can we define oscillator, is a circuit which can convert the DC signal into AC signal. And the potential application of oscillators are timing signal generators. We are using a lot of systems like, even in our laptops or any electronic gadget that you can think of, these timing signals are quite essential. So if we look into the basic classification of these timing signal generators, one is crystal oscillator. Typically, this is what we use in our laptops, which is very, very stable. Typically, it generates signals in the range of megahertz. On the other hand, LC oscillator, this is also quite popular and easy to implement. They are very simple in design. But the thing is, when we want to have on chip, the inductance is very bulky and it is leaky also. So it's very challenging to get high quality inductance. So for integrated solutions, this is not the best way. The other category, what we can think of is a ring oscillator. They are again simple in design. They can even generate high frequency. Here we have a lot of freedom. Here I'm going to focus on these ring oscillators. My research team has designed a lot of oscillators. We are going to see them shortly in the coming slides. The other designs include voltage controlled waste oscillators. These circuits are having moderate complexity, and of course they are flexible. They have a better tuning capability as well. However, focus of this talk is going to be on ring oscillator with different semiconductor technologies because of its simplicity, and it is also capable of generating high frequencies. That's the reason we are considering them here. We all are quite familiar with the ring oscillator. Basically, odd number of inverters connected in a fashion of ring. Here we are seeing a three-stage ring oscillator. The functionality is as follows. Of course, for the CMOS inverter, the schematic is given in the bottom down, where it is implemented with one PMOS and NMOS. Now, so we know the basic functionality of the inverter, which converts or which inverts the input signal. If we apply logic 1 at the input, it gives logic 0 output and vice versa. So when we are having a series connected odd number of inverters, what happens at the output is that the output is going to be inverted every time. This is how we are going to generate logic 0 and 1. Logic 0 typically corresponds to 0 volts, but of course it depends on the design, and logic 1 corresponds to VDD. So the signal is going to oscillate in between 0 and 1. This is the basic principle of a oscillator. Here, of course, we can use any odd number of inverters. For the sake of simplicity, I am just demonstrating with a 3-stage, but it can be like 5-stage, 7-stage, 9-stage, and so on. Now, we are going to look into the low power ring oscillator for IoT applications. So typically for IoT applications, especially for these RFID tags and so on, we would need a frequency of operation in between 10 megahertz to 1 gigahertz, depending on the type of RFIDs that we are using. Okay, basically, which means that we need to generate signal in this frequency range. Of course, we know that clock generators are important functional blocks. Here we are seeing the circuit schematic of a 7-stage ring oscillator. This is a conventional design. There is no novelty in this. It is just that the inverter is being replaced with the CMOS implementation with one NMOS and one PMOS, and the output of the inverter is the last stage inverter is being connected to the input, so that we are forming a ring. Since there are odd number of inverters, we would tend to see oscillations. As simple as that. Now, how to come up with the low power design, and why do we want to have low power? So it is very obvious that when we have battery assisted systems, and if the circuits are draining a lot of current, what happens? The lifetime of the battery is going to be compromised. So always we need to minimize the power consumption. Similarly, even for biomedical wearable applications, or even for biomedical implants, having low power is quite essential. So one of the low power design is using current starving method, in which what we do, we will bias the ring oscillator with very low current, so that the transistors are going to operate near weak inversion. So as you can see, the biasing is being marked in this rectangular window, where the input current is being provided, and it is being mirrored with these biasing transistors M9, MBN9, MBN8, and for both NMOS and PMOS in the top, like the biasing transistors which are marked in the top, the PMOS is in the top and NMOS in the bottom, the current is going to be mirrored here. So we have the control on the current, how much we want to provide to the circuit for biasing. By reducing this biasing current, these transistors are going to be biased near weak inversion, and power consumption can be significantly reduced. Of course, here what is the trade-off we are going to have in analog design? As we know, when we are trying to optimize one parameter, it is going to trade off with other parameter. Here, when we are trying to trade off with power consumption, it is going to trade off on the frequency of operation. But for the application under consideration, especially for this IoT applications, we would at least need megahertz, tens of megahertz to gigahertz frequency generation. Though we are making effort to minimize the power consumption, this is going to lower the frequency of operation. So are there any other techniques where we can get low power but with reasonable frequency for the given application? We are going to see them in the coming slides. Here, two designs we are seeing. These are known as skewed design. The top circuit schematic is corresponding to PMOS skewed design, and the bottom circuit is corresponding to NMOS. There is a typo, I'm sorry about it. So as you can see in the top circuit, for the PMOS transistors, which are labeled as IP1, MIP2, and so on, for them, the input is not being given from the output. In the conventional design, what happens is that the output is being given as input to the very first stage. But instead, here what we are doing, the intermediate generated signal is being given as input to these transistors, which means that the signal doesn't need to propagate through all the stages. So this helps to improve the frequency of operation. This is known as skew design. So this skew design can be introduced for the PMOS or NMOS, as we are seeing in these two schematics. So with these skew designs, we are able to improve the frequency of operation, and with the previous scene design with the current starving, we are able to save the power consumption. Then what we have done, we try to integrate these two techniques to take the advantage of both of them, meaning low power consumption and high frequency of operation. That's what we have done here. So we integrated this current starving technique with the skewed design. Here I'm just showing you a 7-stage NMOS skewed current starved ring oscillator. And then this has been implemented in a 65 nanometer technology, UMC 65 nanometer technology. Here we can see the functionality of this low power RO. Here, for a fair comparison, always we have to implement the designs under the same environment and compare. As we can see, the conventional design, which is marked as this blue line with the circle, here we are seeing the power delay product. The lower the power delay product, the better the design is, right? As you can see, the conventional design, CS stands for current starved design, NMOS skewed, PMOS skewed, and then the last two are the novel designs that we have implemented, that is NMOS skewed CS, PMOS skewed CS. These last two designs are showing relatively low power delay product, meaning their performance is much better than the other conventional designs. In fact, it is preserving the advantages of both low power as well as high speed. In the right side figure, we can see the frequency response of the oscillator. These designs have been tested at 1 volt power supply. Almost, more than 90% of the swing we are getting with both PMOS skewed current starved ring oscillator as well as NMOS skewed current starved ring oscillator. So we are getting very good swing, as well as you can see, the frequency of operation is also in terms of hundreds of megahertz. And then we have compared this power delay product under the same condition. As I mentioned, these designs have been implemented in 65 nanometer technology with a power supply of 1 volt. As we can see, the last two designs, which integrated the skewed technique with current starved, they are showing better power delay product. So they are better than the other designs. So they are very good fit for these IoT applications. This work is actually done by one of my master student. And then I'm going to introduce a new technology now. Like, we are quite familiar with this standard crystalline silicon based technology. And now I'm going to introduce a technology which allows flexible electronics. Even these flexible electronics are also finding potential applications in IoT. So they are important building blocks in creation of sustainable and interconnected world. And these electronics, they they act as fuel in the IoT technology in helping, optimization of production process of companies and industries, and the management of services and infrastructures, limiting the consumption of resources and pollution. So, as we know, the ring oscillators or the clock generators are fundamental blocks in any of the electronic system, including IoT. Now, we are going to see where these clock generators are being used in the IoT systems, and few details on the implementation, even measured response also we are going to present, which some of the new designs which have been developed in my lab. Okay, so here we can see a pictorial representation of flexible electronics in IoT, how it can be useful. The bottom layer consists of devices, sensors, meters, and so on. Once the data is being acquired from these sensors, from the physical process, then it will be subjected to the routing transmission through different means that we can see in the blue box. So we are just focusing on the bottom line, which is marked in the red color. So this is the place where these flexible electronics will come into picture. Now we are going to see some motivation about these flexible electronics and how they are different from rigid electronics, what are their niche of application, and how they can be used in smart sensing systems. So basically in smart sensing system, we measure some physical property without manual intervention, like in any automated way we should be able to sense any physical process. As we know, the conventional practice or the traditional practice used to these rigid silicon integrated circuits. We are quite familiar with them and we see them in our day-to-day life. Now, in niche of applications where we need compact, robust, low-cost systems, we would need flexible electronics. But then, getting everything on flexible substrate is very, very challenging. Circuits with flexible electronics, and post-processing is being done with the rigid electronics. We call them as hybrid systems, which includes two different semiconductor technologies or two different platforms. This is a hybrid solution. The third solution is completely flexible. You can see the wafer here, which has been designed by my PhD students. This can be used for smart sensing application, means truly flexible smart sensing applications. This can be used for smart packaging to sense the or monitoring conditions of different items, like smart packaging, or for variable applications and so on. This is a 30 micrometer thick polyimide substrate which consists of lot of circuits, and it has been fabricated at Pragmatic, UK. Then we also see a few advantages of these smart sensing systems and their requirements. Basically, they should be flexible, compact, and lightweight. And they should be, of course, cost-effective, reliable, and robust. To implement flexible electronics, we can't use conventional silicon technology. Why? The fabrication temperature is about 1000 degrees for silicon. So flexible substrates can't withstand. Then researchers came up with new technology. One of the technology is oxide TFTs. Of course, there are other semiconductor technologies. They also allow flexible electronics like organic, amorphous silicon, and so on. But compared to those TFT technologies, oxide TFT technology is much better in terms of mobility. Its mobility is greater than 10 centimeters square per volt second. On the other hand, for organic or amorphous silicon TFT, the mobility is about only 1 centimeter square per volt second. The mobility reflects in speed of operation. So when we are designing circuits or systems for specific applications, we need to meet its requirement. Like we want to say, for example, we want to design a clock generator which can generate 10 megahertz signal or 20 megahertz signal. If the mobility of the transistor is very low, it's very challenging to meet that requirement. This ICO technology is relatively better than other TFT technologies which can allow flexible electronics due to its improved mobility. And here we can see the transfer characteristics of the device as well as a cross-sectional schematic of the transistor. This is essentially a field effect transistor, meaning we can control the current flow by means of the biasing voltage. Here, where the blue line is showing glass or plastic. This is a substrate. And then on top of the substrate, there is gate electrode. On top of this, there is a dielectric. And then there is a semiconductor, and source and drain are placed on top of the semiconductor. So now when we apply positive voltage to the gate, what happens is electrons are going to be attracted towards the dielectric semiconductor interface. And when we apply positive voltage at the drain, the electrons are going to be drained out and we can see a current flow. Basically, this is a field effect transistor and we call it as bottom gate staggered TFT structure. As I mentioned, like when we are gaining something, there are some trade-offs. So what is the trade-off with this technology? It is having only single type device. There is no stable complementary device. So whatever circuit design we have to carry out, that should be entirely with P-type.
Ma'am, sorry for the interrupt. Sorry for the interrupt, ma'am. Sorry for the interrupt, ma'am. PPT is not clear, ma'am. It is blurred.
Blurred? So
Yeah.
Ma'am, you can turn off the video, ma'am, so that bandwidth can be placed well.
Okay. Just a minute. Are you seeing better now? Sorry. Are you seeing better now?
No, ma'am.
No, still it is
Just
blurred
try to
only.
share the PPT, ma'am. Once share the screen.
So should I have to share the screen?
Yes, ma'am.
Should I
Please
start?
again share the screen.
Yeah. Could you see the screen?
Yes, we are able to see the screen, madam. Please share the PPT. Yes.
Yes. I'm going to share. Could you see the screen better now?
Yeah, we have seen, but it's not clear, ma'am.
Not clear?
Yeah, compare previous, it's okay.
Could you see now or no?
No,
Little
ma'am.
blur is
Still
there, ma'am.
blurred only, ma'am.
Or would you like to share from your side then?
Yes, ma'am. We
Yep.
will share.
From our side, ma'am.
Okay. All right.
Shivshankar, ma'am, can I share?
Please share, sir.
Yes, ma'am. Okay now, ma'am. Is it okay?
Yeah.
Now,
Yeah.
now it is.
I can see the screen, yes.
Sorry, it is clear, ma'am. Clear. Okay, sir.
Okay. Please move on. Next. Yeah, you can stop here, yes. I hope you can hear me.
Yes, ma'am.
Yes.
Okay, all right, yeah. So this Oxy TFT technology is relatively new. So as a first step, what we have done, first we were trying to understand the technology, like what circuits we can design, what is the turn-on voltage, what are the analog properties of the device. Analog properties means intrinsic gain and then on resistance, And the transconductance, all and unity current gain cutoff frequency. First, we have studied the technology, how it is varying with respect to different channel lengths and so on. Then we have developed device models. Actually, this work I have done during my PhD, but of course now commercial device models are also available from foundries. And here the challenging aspect is we have to come up with novel circuit design techniques, because we can't adopt CMOS circuit designs here, because everything needs to be designed with N-type transistors. Okay, please move on. Next. So here we can see some of the technology characterization. We have taken transistors with different channel lengths ranging from 2 micrometer up to 160 micrometer, and we are checking the turn-on voltage, the drain current, the transconductance, output conductance, intrinsic voltage gain, and then unity current gain frequency, and so on resistance also. These parameters are very, very important for both analog as well as digital application. The intrinsic gain, whatever is marked as AV, it's very important because this is the maximum gain that can be obtained by a single transistor. Meaning, if you are having a single stage amplifier, this is the maximum gain that we would expect. As we can see from this table, the AV is increasing with respect to the channel length. But what is the trade-off we are seeing? The unity gain current cutoff frequency is reducing. That is obvious, right? Like when the channel length is high, the speed of operation is going to be compromised. So depending on the application, we have to make the choice what channel lengths we have to use and so on. To get that idea for the designer, we have done this technology characterization. Next. Now, the challenging task is to design circuits with unipolar transistors. Inverter design is very simple with CMOS. We can just take one NMOS and PMOS, and we can get, inverter with very good rail-to-rail operation at the output and very good noise margin and so on. But which is not easy with this technology due to unipolar transistor-based implementation. So obviously the first choice is using a diode connected load. But what is the limitation of the diode connected load? It is mentioned in equation 1. The output high level and low level both are compromised. So when we are applying logic 0 at the input, we are not able to get a strong logic 1. It's being compromised. Always the output is less than VDD. Here the notations are as follows. VOH means output high level, which is equivalent to VDD minus VTH. There is always a threshold voltage drop. It looks simple here, but the thing is, when the signal need to be propagated through many logic gates, every gate is going to introduce VTH drop. So for example, say it is transmitting through 5 stages or 6 stages, meaning 6 times VTH drop is going to be there. So after 7th stage, we can't really see the logic high level. Similarly, logic low is given by VDD minus 1 over GMT2 times IDS. When we apply logic 1 at the input, we are not able to get strong logic 0 with this configuration. This is more than the reference level. So again here, when it is passing through different stages, we can't get complete a digital operation. It can even lead to malfunctionality of logic gates. So this is not a robust design. Then people started mimicking CMOS with only NMOS. That design is known as pseudo CMOS, which is shown in circuit B. So the bottom transistor T1 is very same as in the CMOS design also, but the top transistor T4 together with an inverter before mimics a PMOS behavior. So it is as good as a CMOS design, but of course here everything is being implemented with NMOS transistor, so we call it as pseudo CMOS structure. Here the beauty is we can get strong logic 0, as we can see in the equation 2. We can get strong logic 0, but logic 1 is being compromised. Logic 1 is equivalent to VDD minus 2 VTH. Then another configuration is bootstrapping configuration, which is marked in this rectangle. Here we can get strong logic 1, but logic 0 is compromised. Then what we have done, we merged these two techniques like pseudo CMOS plus bootstrapping, with which we are able to get both strong logic 0 as well as strong logic 1. This is almost like a perfect CMOS gate with VDD is with V out high is equivalent to VDD and V out low is equivalent to ground level. Next. So what we have done, we characterized these gates at different power supply voltages. And also we have designed a 5-stage ring oscillator with all these gates, and we were analyzing its performance. We know that ring oscillator is nothing but, odd number of inverters connected in the fashion of a ring. As you can see here, the power supply voltages are quite high. This is work done almost 5 years ago. The time, even the device dimensions are also quite high, so we need to use high power supply voltages like 10 volt, 15 and 20. Among these 4 configurations, the pseudo CMOS bootstrapped configuration is giving very good swing, almost 100% swing, and very good frequency of oscillation. Next. We expanded this technique to other logic gates,
ರವಿ ಹಿಂಗೆ
namely
17 ತಾರೀಕು ಬಂದಿರ್ತಾರೆ
namely
ಸ್ವಾತಿ ಅಮ್ಮ ನಾನು ಹೆಂಗೂ ಸಾಗುದಿಲ್ಲ ನಾನು எனக்கு ಮಾತ್ರ
As
ಗ್ಯಾಸ್ಟ್ರಿಕ್
participants can please mute.
நான்
இங்க யாரும் உள்ள இருக்கிறா
எங்குள்ள ಹಿಂಗ இருக்கிறோம்
Participants are requested to mute.
17 தாರೀக்கு ரவி வராடி ஸ்வாதிவை எல்லா பக்கம் அழிச்சுன்னு போய் சாப்பிடுப்பின்னு சொல்றான் எங்கம்மா சாப்பிட்டு இவளுக்கு அர்த்தமே ஆறுதில்லை பிரதிக்கு லௌகிக்கங்களே அர்த்தம் ஆறுதில்லை
வெளியில நிறைய சாப்பிட்டு இருந்திருந்தா அப்போ இதா இருக்கு நமக்கெல்லாம் ஹவுடுக்கோ எல்லாத்துக்குமே.
Ma'am, you please proceed.
Yeah, please share the screen. Yeah. So we extended this technique to other logic gates also. They also have given very good performance in terms of rail-to-rail operation. Here we can see all the circuit schematics, fabricated micrographs. And in the next slide, we are going to see the measured response. Please go to the next slide. Next. So this is the measured response with all the novel gates. We are getting complete rail-to-rail operation, and with pseudo CMOS and bootstrapped designs, we are getting some compromise in the rail-to-rail voltage. Next. We also have tested a frequency divider by using these pseudo CMOS gates with the help of a D flip-flop. This is also measured response, as we can see here. Actually, we have developed this for a flexible radiation sensing system, which is part of a EU project. The clock input is given by this black signal, and in the bottom we can see the frequency divider functionality with the different power supply voltages, and we are able to get complete rail-to-rail operation with this proposed gates. Here we can also see the fabricated circuit. Next. Yeah. Then what we have done, we were experimenting different techniques to minimize the power consumption of this ring oscillator. In my previous slides, I have shown you CMOS designs. You can keep the next slide. So in CMOS designs, I have mentioned about this current starving technique, skew technique, and so on in 65 nanometer technology. Now we also experimented certain low power techniques using these oxide TFTs. In the top left corner, we can see the proposed schematic where the signal is being skewed. Instead of taking the output from the very last stage, the intermediate signal has been fed to the inputs of the inverters. With this, we are able to see significant improvement in the frequency of operation. Respective micro photographs, like after fabrication, we can see the pictures in the bottom. This work is done by my PhD student. Here we can see the measured data. So we have characterized these conventional ring oscillator as well as this novel ring oscillator. We could able to see that with the novel ring oscillator, the power consumption has been reduced and the frequency is significantly improved. Overall, the power delay product is improved for the this new design. Next. And the reason for choosing this ring oscillator is it has a lot of advantages. It is a very simple but effective circuit. We have developed model for oxide TFT for different temperatures, and of course we have validated the data with ring oscillator, meaning we used those transistor models to develop a ring oscillator, and we extracted the simulation data and we got the circuit fabricated, and we experimentally characterized this ring oscillator performance, and then we have compared the simulation data with the experimental data to validate the model accuracy. Since the circuit is so simple to test, this can be used as a unit cell for testing any platform. And we got good accuracy, almost like 10% accuracy we got. Next. So here we have done very interesting work in which this RO has been used as a sensor. This is a collaborative work with my colleague from chemical engineering department. Their team has developed paper-based fuel cell. Typically, when we want to turn on the circuits, we apply a power supply, right? So here, they have developed paper-based fuel cells. Basically, we want to have everything on a flexible substrate, even the power supply also. That's where this work came into picture. On the paper, they have developed these fuel cells. One fuel cell is not able to, power up the circuit. So we have used a series connection of two. You can see it's a schematic over here. The output of this stack is being given as power supply to the ring oscillator. You can see that the supply voltage is about 1.4 volts and it is able to drive the circuit very effectively, and we could able to see good frequency of oscillation. Here we are showing that the paper-based fuel cells are able to drive the flexible electronic circuits, and we also have shown its application as sensing. Next slide, please. Next slide. So what we have done, when we are changing the concentration of uric acid in the paper-based fuel cell, the voltage generated by the fuel cells are varying. So when that voltage is varying, the frequency of oscillator is also varying. So this acts as a potential readout circuit. By using post-processing, we can even have a compact point of care devices. This work got recently published. Next. Yeah, so with this, I would like to conclude my presentation. So here we have seen ring oscillators with CMOS technologies, the low power ring oscillators with skew technique, current starving technique, combination of these two techniques in 65 nanometer technology implementation. Then we also have seen the ring oscillators with oxide TFTs on flexible substrates. Here we have seen a lot of designs like the conventional designs, novel designs, and so on, and their experimental characterization. Next. So here I would like to acknowledge the funding agencies, SERP Power Fellowship, and our institute ISA Bhopal, and WISER from Indo-German Science Technology Corporation, and the industry partners InnovaFlex, SEL Chandigarh, and the international collaborators, my PhD students and master students, and all the researchers that who contributed to this research work. Yeah. Yeah, thank you. And I would like to take questions from the participants.
Are there any queries from the participant side? Sir, in chat box, is there any queries, sir? Anil sir?
Yes, ma'am. One question is there, ma'am. Ma'am, in 64 nanometer technology, how we will increase the processing speed?
See, as a designer, we can increase the speed by using circuit design techniques. For example, we have seen this skew design, in which we are not taking the output from extreme output, rather we are using intermediate signals for the inverters. So there the signal doesn't need to propagate through all the stages. Okay, so when we are reducing the propagation time, it adds to the improvement of frequency of operation. This is just one technique I have shown, but with other different techniques we can improve the speed of operation. These techniques can be explored in any technology. No need to just limit to the 65 nanometer. Again, here I just have shown only for the ring oscillator. For example, if you take amplifiers, what you can do is that when you want to have high gain amplifier, the best way is to cascade low gain amplifier so that you can get higher bandwidth as well as higher gain. So depending on the type of design that you want to have, you can experiment different techniques.
Thank you, ma'am. Any questions from our participants? You can unmute and interact with speaker.
Ma'am, thank you for your presentation, ma'am. I have a small question. Ma'am, RO is applicable for agriculture. As you said, one sensor, it's RO, resistive optic sensor, I think.
Ring oscillator, ma'am.
Ring oscillator. The RO is ring oscillator. For example, if you want to,
it is not a sensing element, is?
It is a readout circuit. Of course, it can be used for sensing. In the last few slides, I have demonstrated its application for sensing. For example, like what we have done, our colleagues have developed paper-based fuel cells. Okay, and also they have developed some electrochemical sensor to sense uric acid. When they put the uric acid, I'm explaining with the example of uric acid, but it can be generalized to any other application as well. So when the concentration of uric acid is changing, the output voltage or the output current of the electrochemical sensor is changing. So what we are doing, the output voltage we are applying as power source to the ring oscillator. What is happening now? This ring oscillator frequency of oscillation is changing. So this ring oscillator is sensing the physical parameter in terms of frequency. So it acts as a readout circuit.
Ma'am, one more question, ma'am. As you said, okay, ring oscillator is nothing but an inverter. Yes?
And it is a odd number of inverters connected in a ring fashion.
No, ma'am, you said it's a CMOS structure, as you mentioned, for a ring oscillator. It has one PMOS and one NMOS.
Yeah, that is inverter. Inverter
Yes,
is a
ma'am.
unit.
Yeah. That is equal to ring oscillator, or?
No. Single stage inverter we can't think of inverter. Like
Because as you said, it's oscillation. When you apply 0 to the input of the inverter, it will produce 1. Again, the same, it will be cyclically happen. Na?
Yeah. See that, yes, you are technically right, but the fact is that the gain may not be sufficient. So you can, I have shown oscillator response.
Yes.
With CMOS, I think we have used 7 stage. We were able to get a voltage swing of 92%, in between 92 to 98%. That is for 7 stage. If you are just using 1 stage, the gain is going to be significantly compromised. You can't really use it as a clock signal.
Okay. Thank you, ma'am. Thank you.
Yeah, it's like this. Like when you are connecting something in series, right? The gain is going to be multiplied when the signal is propagating in different stages. When it is being multiplied properly, you are going to get complete, you are supposed to get a square waveform. Oscillator is essentially a circuit with a gain of infinity, right? Which converts the DC into the clock signal.
But in my question is, ma'am, it's oscillator is not a stable movement, yes? But the inverter output is be unstable, either be 1 or be 0. But it is oscillating. We cannot say it's a step, we cannot calculate the value of that.
Yeah. So for inverter, like how you are going to test, you apply the stimulus at the input, right? And you notice the
Yes.
output. But invert for the oscillator, we are not going to give any input signal. It is just the power supply that you give.
Okay, okay.
Yeah, just note the difference.
Okay, thank you, ma'am. Thank you for your sharing.
Thank you. Yeah.
Ma'am, is it possible you share your mail ID, ma'am, for further
Yeah,
clarification
sure.
and further
Yeah,
implementation?
sure. Yeah, sure. Any other questions?
Ma'am, in one slide, there is a measurement setup with the proposed design. So at the right side, one equipment is there, ma'am, which the circuit is fabricated circuit is mounted. Can we know the name of equipment, ma'am?
Probe station.
Probe
Actually,
station.
we have customized it for our applications.
Okay, ma'am.
Ma'am, one more question, ma'am.
Yeah.
In CMOS logic, how we can eliminate the skew, ma'am? Because it has high skew, low skew, and no skew. It's unskew. Skew is nothing but a glitches, yes?
Can you repeat
So,
your question? Skew is nothing but?
glitches, distortion.
You see, it really depends on the design where you are applying the timing signal. And the transmission path, everything adds to the skew. It depends on the architecture that you are considering. And of course, like, what is that? When you are designing an inverter, no, you know that NMOS and PMOS are having different mobilities. So you need to take care of the aspect ratios to compensate this mobility variation so that you are going to have a symmetric waveform. On the other hand, depending on the system or architecture that you are considering, you have to take certain precautions to minimize the skew.
When we can maintain the aspect ratio is equal.
No, aspect ratio should not be equal. As you know, like for N-type transistor, the mobility is 350 centimeters square per volt second. For PMOS, it is 100 centimeters square per volt second, meaning P is weaker than N. Okay. So to compensate this, you have to make sure that P is wider than the N to have symmetric rise and fall time.
Ma'am, I studied on condition, ma'am, from Neil Engage University. It is CMOS VLSI design. From that, they mentioned the ratio of beta P by beta N is greater than 1, it is goes to high skew. When beta P by beta N equal to 1, it is unskew. When beta P, the ratio of beta P by beta N less than 1 is low skew. So in this middle condition, beta P by beta N equal to 1, it is unskew. How we can able to maintain this condition, ma'am?
See, as a designer, you have control on the aspect ratios of the device. Okay, for digital circuits, like you don't have much control on the biasing voltage. It's either you have to apply logic 1 or logic 0, which is very different than the analog design. So basically, you have to play with the aspect ratios of the transistor and the technology that you are considering.
Okay. Thank you.
Now, one question is there in chat box. The post layout simulations shows different results in comparison to pre-layout simulations due to parasitics. How can we reduce the effect of parasitics so that pre and post layout results remain same?
So that is obviously by using effective layout techniques. So we have to optimize the layout design to make sure that the schematic simulations are in agreement with post layout.
Okay, ma'am. Okay. Shivsankar, ma'am.
Yes, sir. Sir, you can
Question
proceed with this
is...
concluding remarks, sir.
Yes, ma'am.
Ma'am, one more question, ma'am. One more question, ma'am.
Sir, please. Carry on. Selvin, sir. Dr.
Shall I
Selvan, sir?
proceed? Yeah, shall I proceed?
Yeah, please continue, sir. Go ahead.
Yeah, ma'am, I think that today webinar topic is low power RO for IoT applications.
Right.
I think you are not given much importance to IoT.
See, in the CMOS, whatever we have discussed, that is for IoT applications where the signal frequency is in the range of 10 megahertz to gigahertz. Okay. Now, in IoT, like RFID is very, very important aspect where the clock signal generation is very important and it is one of the essential. Then in the flexible electronics, which are going to be used for RFIDs, there also we need clock signal generator. That's where I have explained different RO designs with oxide TFTs for RFID with 13.5 megahertz frequency of operation. With CMOS, yes, we can go up to gigahertz operation with the different kinds of RFID. So again, like, depending on the type of applications for IoTs, in which like RFID plays a key role, depending on the frequency of operation, certain different technology will be quite useful. For example, if I want to make a gigahertz frequency with oxide TFTs, that's not possible. And if I want to have flexible electronics for given application for IoT, I must have to use flexible electronics. So I just try to have a blend of both CMOS as well as oxide TFT for IoT applications, mainly focusing on RFID clock generator. Did I answer your question?
Yeah, I got it, ma'am. Got it. Thank you. Thank you.
Anil sir,
Thank you,
you
ma'am.
proceed, sir.
Thank you, ma'am. Good evening, everyone. It's my privilege to extend a heartfelt vote of thanks and concluding remarks to today's session and to our esteemed speaker, Dr. P. Ganga Balendri, madam, for delivering such an insightful and enlightening talk on low power oscillators for IoT. Your expertise and in-depth knowledge have truly illuminated the critical role of low power oscillators in advancing IoT applications. The way you broke down complex concepts starting from basic classifications, low power ring oscillators for IoT applications, and shared practical insights on flexible electronics challenges, smart sensing systems, how it will be, and the requirements, temperature dependent behavior modeling, and validation for oxide TFTs, applications of ring oscillators in sensing has not only enriched our understanding but also inspired us to explore innovative solutions in this fascinating domain. We are deeply grateful for your valuable time and effort in sharing your wisdom with us today. Your session will be undoubtedly resonate with us as we continue our journey of learning and innovation. Once again, thank you, ma'am, for your presence and making this session truly memorable. Thank you all the participants for truly involved in this session. Thank you, ma'am.
Thank you, ma'am, and thank you, ma'am, and thank you, sir.
Thank you, ma'am.
Thank you, ma'am. So I can disconnect, right?
Yes, ma'am. Yes, ma'am. Thank you for spending your time, ma'am. We really feel honored to have you today with us.
Ma'am, share your mail ID, ma'am. It's possible you share your mail ID.
Yeah, thank you so much.
Thank you, ma'am. Thank you.
Susankar, ma'am.
Yes, ma'am. Yes, sir.
Ma'am, next speaker join, ma'am.
Yeah. Well, let me check, sir.
Yes, ma'am.
Next session is Nal Subramaniam Garu.
Yes, ma'am.
Let me check, sir. Was there, sir?
Yes, ma'am.
Ah, so guest has joined, huh?
One second, ma'am. He said I will join. I'm in front of laptop. I will join within say a minute.
Sir has joined.
Okay.
Good
I joined.
Sorry? Hello, sir. Good evening, sir.
Yes, ma'am. Good evening. My voice is audible?
Yes, sir. Yes, sir. It's audible.
Okay, ma'am.
Shanmari, ma'am?
Yes, ma'am.
You can go ahead, ma'am.
Yes, ma'am. Good evening, all. It is my pleasure to introduce today's resource person, Mr. Nagasubramaniam, sir. He is currently working as a senior design verification engineer in VLSI at Digicom Semiconductor Private Limited with over 2 years of experience in design verification and a strong background in academic teaching. Sir has brought a blend of practical industry experience and a deep understanding of electronics. He has successfully completed 3 VLSI design verification projects, contributing to the verification of complex systems and ensuring their functionality and performance. Sir has proficient in key design verification tools and methodologies, including System Verilog, UVM, AHV, AXI, cache memory verification, and verification IP development. Sir has expertise includes power-aware verification related to UPF and ensuring low power consumption in design systems. His technical proficiency extends to debugging, simulation, and the verification of complex designs, which are critical for verifying integrated circuit designs and ensuring they meet desired specifications. Before transitioning to the industry, Sir has worked for 4.5 years as an assistant professor in the ECE department at IIIT Srikakulam, where he mentored and guided students in advanced electronic topics. Sir has published 3 IEEE conference papers and 1 book chapter with IGI Global Publisher, contributing to the field of electronics and design verification. These publications reflect his commitment to advancing knowledge in his field and staying updated with latest developments. Currently, Sir is enhancing his expertise in design verification, particularly in complex systems such as memory interfaces and power-aware designs. Thank you for joining us, sir. Please continue the session.
Sure, ma'am. Okay. Are you able to see my screen?
Yes, sir.
Yes, sir.
Okay, ma'am. Okay. We this I hope you guys all know about VLSI. These are the various fields which we are having in the VLSI domain. Okay. Which is a industry is actually very large scale. Scale is very large, but the age of the industry is very small. You can see here all the front end domains. Okay, in this I'm working in the verification domain. There is another domain also, which is backend domain, uh, which is mostly depending on the physical things. Okay, this front end is mostly depending on the a kind of a simulated or tool based. Few domains are tool based. So if you see here, actually it will start at the architecture level initially. Later it will come to the design level. After that it will come to the verification level. In the verification there are different ways of doing things. After that it will come to the various levels of uh, checking kind of things. After that it will come to the fabric kind of thing. Then it will come to a physical thing. That's how chip processing will be done. In this design and verification, both are hand to hand. Okay, suppose if I'm going to verify one chip, so we have been in touch with the designer continuously. Okay, suppose they'll give one kind of release, means they'll give one kind of RTL, and we will verify that RTL in a different aspects. For that we will develop a particular plan. I'll go through all those things in the next slide. Briefly I'm telling how design and verification are hand to hand. After that we will verify required features only. I'll come to what kind I'll come to what kind of features. Okay, after that we will if we find any bugs, we will report those bugs. According to that they'll change the RTL, again they'll release. Okay, again we will apply what and all the plans we previously verified. So like that it will go hand to hand. Okay, so let's see, this is the thing in brief. Let's focus on the verification. Okay, this is the verification flow. I hope most of you are aware of it. Okay, first we'll sit with the manager level verification architecture. Then we will plan accordingly what and all the items we need to verify. I will show you how the plan will be, how a verification plan will be. After that we will develop the environment, which is called test bench. I think most of you are worked on design, and most of you using a Verilog language. I think you designed some of the designs. But when it comes to the verification, we will write a very small test benches in our academic level. But when it comes to the industry, verification is entirely different ball game, and it's a different aspect. Okay, for this we have a separate language. Okay, I will show you what and all the language and scripting things are available, are required to be a verification engineer, successful verification engineer. In this test bench, we will develop some of the test cases. Okay, these test cases are tell us to verifying a particular feature of the design or not. Okay, so if we found if we find any bugs, we will report to the design. Okay, if is there any issues in the design, or if is there any issues in the test bench, we will cross check those errors, and we will enhance the test bench. That's called a debugging process. Okay, while you are doing debugging, you will get the bugs will be reported to the further, and RTL will be updated. Same test cases we will run on those things. Okay, there are some things which are makes our verification journey as comfortable as possible. Those are called as a metrics. So under that metrics we will see the coverage. I will tell you the what is the coverage in a basic level, I'll tell you. Once we verify all the features, we'll come to a place called closure. Okay, this is the verification closure. Okay. Okay. See here, these are the various types of verification engineers. Okay, it's not a thing like one man army. It is a requirement of many other points, many people efforts. Okay, entire verification is of two types. Okay, that is top level verification. Another one is leaf level verification. I'll tell you what is top level and what is leaf level. For a time being, if you can understand this. Okay, there is a kind of a thing called digital verification. In that unit block will be there, subsystem level will be there, top level will be there. This AMS is nothing but a digital and analog both mixed signal verification. Okay, and okay, then see whatever the verification we are doing, which is of several types, but on a lighter note, we can tell it as a functional verification. Means how RTL function will be, what are the various functions of the RTL we are going to verify. Okay, there is another thing called sign-off verification. Okay, in this sign-off verification, we will go by the gate level simulations and emulations. Physical verification is for hardware. Many more kind of things are there. Okay, these are last level of verification. Okay, entirely different teams will work on these things. Functional verification will be done by one team, GLS will be done by one team, emulation will be done by one time. Every field has its own way of doing things, and they have their own structures, and they have their own environments, they have their own tools. It's all different one and another. Okay, see, these are the various languages which we are currently working on those things. Okay, see, one is system Verilog. So you guys all know about Verilog, but if you use Verilog, the scale of the test bench is very limited. That's why people are not at all preferring nowadays Verilog for the verification. Okay, we are completely depending on the language called system Verilog. Okay, see, if you see here, these are the things yesterday, means history. This is the current trend. Okay, we are going the system Verilog only. uh, there are so many enhancements done from the Verilog to system Verilog. Most of the features they carried, but we can say that the advanced version of the Verilog is system Verilog, and they introduced many more things. Okay, what and all the various things they introduced from Verilog to system Verilog, we'll see in the coming slides. Okay, but nowadays most of the designers are using system Verilog for their design also, not only for the verification. System Verilog, it is there for the design also. Okay, some people are still working on VHDL. I hope it is in near future it won't be there. I'm sure. So if you see this UVM, this is not a language itself, but most of the people are thinking that UVM is a language. Okay, it's not a language, it's a methodology which took it from the system Verilog. Okay, uh, in a system Verilog there is a thing called object oriented programming. Programmings are two different aspects programming is having. One is object oriented, another one is aspect oriented. Okay, currently the verification environment world, design verification world will be object oriented programming only. Okay, in that using that object oriented programming structure, they created a methodology called UVM, which is a universal verification methodology. It's not a language. Okay, see, you can see here methodologies. One of the methodologies is UVM. There are so many methodologies, which is OVM, RVM, VVM. At the final is UVM. Now the current trend is UVM only. All those are history, but UVM is current trend. Okay, and if you guys already having any knowledge on the scripting languages like Perl, Python, okay, Linux, Make language, these are the various these are the scripting language which we are using in the verification environment. See, that's how the scale will go from the smaller node to very larger node. Okay, all these scripting languages will use it to develop the environments. Using a scripting language, we can develop the environment. Later, we will add whatever we want to that environment. Okay. See, at the end, what is environment? It is a kind of a module. It is a kind of an entity. See, I think you guys are having a knowledge on Verilog. Verilog is having a entity called module. So at the end, the environment is module only. Module or some other kind of entity. So those modules will be generated by our scripting language if we want. Otherwise, we will write our own environment. Okay, these will help you a lot, and these all are mostly are open source. You can go by it, and you can easily understood, and you can use those applications in the environment. Okay, when flow is going on, I will tell you how I used these things, these scripting languages in a various places in my last project, so that you can understand how scripting will be helpful for us to verify the design in the larger node. Okay, and coming to this, these are the various companies which are currently developing the tools for the verification as well as design also, but I'm not much aware on the design tool companies, but as of I know, we are having Aldec, Rivera, and Synopsys, Cadence, Siemens. These are the various major companies which are providing the tools for us to verify the design. Okay, whatever the language is there, the language can be approved by the IEEE. Based on that manual only, these tools will develop the language. Okay, yeah, you can use the simple. You need to purchase any tools. Okay, it is available in the EDA. Okay, these are the various tools available in the EDA for us. But this Aldec is available only for Gmail. If you have any institute mails or industry access in industry mail things, then remaining three also will be available: Cadence, Mentor, Graphics, and Synopsys. Okay. See, here I used a word called compile and simulate. Okay, I'll tell you in a lighter way. So the entire process of verification is of 3 steps. One is compilation, another one is elaboration, another one is simulation. Okay, initially in the compilation level, we will check the syntax level things. Is there any syntax mistakes are there, or is there any wrong way of writing language? Those things will come under the compilation. Once it will compile once it compiled all the modules, it will stitch the modules. Means first which module has to come first, which module has to come, like that. One order will be there, that is called compilation order. That order will be verified in the elaboration level. Once it is done, they'll start simulating the data. Means they'll put the data from the verification environment to design. Okay, you will get to know that soon. Okay, these are the various other tools also be there. Okay, and we can, if anything is wrong. So can anybody tell how many different ways are there to uh, understand the design? We have several ways. I'll tell you very few things. One is uh, the way module is producing the output. By seeing the output values, we can understand what is happening. By seeing the waveforms, various signals are from the design. By seeing the how the signals are changing by waveform, we can understand. Okay, uh, and for a different kinds of inputs, it can produce a different kinds of outputs. The various kinds of outputs, by using that also we can understand the function of the module. Okay, and by applying several conditions on the design, and we can understand how design behaves for those conditions. Like that also we can understand the function of the design. Okay, and we can generate the random data, and for that random data how design is behaving. By that also we can understand the function of the design. For all those things, there are several tools are there. Okay, if you work on a real cadence tool, it will provide all these things. Okay, it will provide a waveform debugger, it will provide a xtracer. Okay, like this. All these things are internal features to these tools: cadence tool, mentor graphics tool, synopsis tool. Okay, see, this is one SOC. This is one SOC. Okay, can anybody tell me what is SOC? Do you have any idea?
System on chipset.
Yes, correct. System on chip means on a chip we can see the entire system, right? If you see here in the at my cursor here, our CPU will be there. Means this is a different story. It will be different from the particular design to design. Okay, here whatever you are seeing, this is not at all a design. Okay, it's not designed by anybody. It is a simple way of making you to understand what is SOC. Okay, see here, this is CPU, means where processor will be there. Okay, it is coming up with not only single core. Now they are having 8 cores. Okay, each core come up with its own memory. Okay, all the memories has to be interconnected, so then we have a cache coherent kind of thing. Okay, this is the part. Okay, and here whatever the requirement based on the design, as per the architecture given the requirements to the designer, based on that these application specific components will be there. Okay, uh, and here you can see a DDR. Okay, double data rate, and this is USB. Okay, this is PCI, Ethernet. Okay, all those respective layers will be here, and here some of the other kind of peripherals. Okay, WLAN, SATA. Okay, HDMI, LTE, all these things will be here. These are the various low speed peripherals like GPIO, UART, I2C, SPI. Okay, power management unit. Okay, tomorrow session I'll tell you how power management unit will work. Okay, and this is another way of representing the SOC. See here, this interconnect. This interconnect is nothing but a kind of a fabric. Means the way we want, the interconnect will change the circuit and it will route the data. Suppose CPU wants to access the one of the peripherals in this low speed. So inside this NOC, there are so many routing algorithms will be there. It's all our digital logic only. Okay, from here it will route the data through this NOC and it will use any one of it, or it will consume data from any one of it. Okay, and it has its own cache memory. Nowadays these NOCs are very, very powerful. Okay, those NOCs are itself a big systems. Okay, then you can call those things as a sorry, I used a word called NOC. NOC means network on chip. Okay, these are the different subsystems. Okay, all these subsystems are connected using a thing called NOC, network on chip. Okay, so data will be routed from one place to another place. So now the point is, each subsystem will be verified by different teams. Okay, CPU subsystem verified by one particular team. Low peripherals will be verified by one particular team. High peripherals, high speed peripherals can be verified by one team. NOC will be verified by one team. Okay, all these, each subsystem will be verified by different teams. Okay, that is one point. Another point is, all these things will be verified in a single shot. Okay, means how subsystem is taking the data from the low speed peripherals. Okay, how low speed peripherals are accessing these application specific components. So the connection between them, the routing algorithms between them will be verified on the top level. Okay, so I hope you got the point. Top level verification is different, subsystem level verification is different. Subsystem level verification means you will verify the particular subsystem. Okay, top level verification means the connection between the subsystems we will verify, nothing more than that. Okay, this is one more CPU. Sorry, this is one more SOC. This is another kind of SOC. Based on the applications, these SOCs will be changed from one point to the another point. And if we want me to put a note on this thing, nowadays they are introducing the machine learning and artificial intelligence kind of methods into the chips, so that the complexity of the SOCs are taking its next level. Okay, previously the SOC level is very, very small. Okay, nowadays they are introducing so many subsystems into the chip, and they are making things so much complicated, so that the verification also be very difficult to verify that particular SOC. Okay, so so I hope you understood the point in terms of machine learning and algorithm. Sorry, artificial intelligence, because now they want a compiler. For example, if you take a point like they want a compiler which can compute more than 1 trillion or more than 1 trillion operations in 1 second. So that imagine how that SOC will be. Okay, how that SOC design will be, how the verification of that SOC will be. Okay, so that is the scale now. See, you know this thing, automotive semiconductors, like we have a car which is coming with a many features which are mostly automotive in nature. Okay, and car is having a one particular kind of a system, radar system. It will understand the objects around it, and based on that it will take the decision. Okay, for that they have one particular chip. Okay, to manage the entire power of the car, battery power of the car, or internal powers of the car, they have one particular chip. Okay, like that, every feature nowadays, every feature is a kind of a chip. Okay, so we have a large scope on the design, and we have a more than that in the verification. This is a kind. So these are the various things which are coming with the coming with a system. Okay, it may have CPU, it may have NPU, it may have a GPU. Okay, network processing unit, graphic processing unit, so many IPs. Okay, as of for last 3-4 years, the IPs are like SPI, I2C, UART, Ethernet. Those are the IPs. Nowadays, they are coming with their own designs and they are projecting them as a IPs. Okay, see, verifying the existing IPs like SPI, UART, I2C is somewhere the other it is okay. We can verify. But when you come up with your own design, it is a bit complex to, and we have to think more combinations how to verify that a new kind of IPs. Okay, we have so many protocols. I will tell you what are the various protocols we are having. So the big thing is interconnect. How all these subsystems in SOC are interconnecting each other and how they are exchanging the data. At the end, what is the digital system? Digital system is nothing but a garbage in, garbage out. Whatever you are putting, that will come or that can be manipulated. Okay, so the most important part of the SOC is interconnect. Okay, so if you want to be increase your scope of the research, so I am suggesting to work more on the NOx, because uh, anybody can do the IPs. If I want a one particular application design, I can say I can try to design using a Verilog or system Verilog. Okay, how this has to be communicate with other things, that is a major part. Okay, I hope you understood the point. I am having a different, see, here so many things are there. Okay, I can put all those things in. It is very difficult, right, to putting all those things in one particular chip. Okay, so automatic, see, we on a bike we are having a ABS, okay, automatic braking system, but that cannot be included in the main chip, right? Sorry, that cannot be a uh, that cannot be as a separate part of the, sorry, how can I tell, that cannot be a main part in the module. It can be a separate module. Okay, and the main module and this automatic braking system module has to be communicate each other. Okay, there are, see, if you see here, all these are each chip. If you see, these many are there, all these things has to be communicate through interconnect only. Okay, so how much intelligent of that interconnect, so the design has to be that much effect, the design will be that much effective. Otherwise it is a normal design like other designs, right? And there are so many communication units. Okay, the basic, if you ask me what is the basic communication unit, is nothing but Ethernet. Okay, and nowadays there so much popularity is coming with the memories. Okay, for example, if you see the Meta, okay, means Facebook, they started design and verification. They entered into a VLSI domain. Initially, I felt like so much strange kind of thing. Later, I understood, because they acquired many things, right? WhatsApp, Instagram, and they are having Facebook. All these are database oriented. They have to be stored, right? Everything. So that for that they need a server. So far they dependent on AMD, this kind of server designers. Now they see, they took a decision like they want their own server, so that those has to be verified, right? Whatever the memories they are using in the server, those has to be verified. Then only they can understand is it is a effective server or not. Okay, based on their requirement, they are designing the server. Those servers has to be verified furtherly. Okay, so like this, many more things will come when it comes to one application. So that's how it works. Okay, and the computing between them is to be much faster, and the power management has to be mm, mm, it power management has to be very sophisticated and optimized. Suppose for example, um, Just wait. Suppose if one part of the subsystem, if one part of the SOC is taking a more power, so interconnect or some other unit in your SOC has that intelligence, so it has to divert the maximum power to that particular subsystem, and it can control the power of the remaining subsystems on a very less kind of a use. Okay, that kind of power intelligence also need to be there. Okay. Okay. So these are the various things which come with the SOC. Not SOC, verifying the SOC, right? The size can be, the SOC size can be very big, right? The SOC size can be very big means it's not a big chip. Okay. See, the chip is always as our see, which is in the nanometer size only. But here the size point is complexity of that particular design. Okay. So in order to verify that, the simulation will take so much time. Okay. Okay. And how the interconnect, okay, how that chip performance, okay. Most of them are having a cache memory, so those need to be verified. Power management challenges. Okay, I discussed all these things. Okay. So these are the these are the various protocols which we are currently using. But for one project, all these are not required. It depends. I am giving a wider aspect. Okay. JTAG, APB, HB, AXI, okay, SPI, I2C, UART, Ethernet, USB, this PCI. Now the current trend is these three. Okay, PCI, Ethernet, and USB. These two are this EAC is very rarely used. Okay, just a minute. Okay, and these are memory kind of a things, DDR and LPDDR. Okay, and these are division of these things. Okay, which one use where. Okay, now the point is we have a IPs, means as I told here, these are the various designs, right? Each design you can call as a IP, intellectual property, means it has some property, means it is coming up with some variables are called as a property. Those variables are work on each other and perform some kind of a operations. Okay, that is called intellectuality, right? So for all these IPs, in our verification, we have a VIPs. Okay, I'm talking two different things here. If you see IP here, it is a design thing. If you see this VIP, it's a verification thing, right? What exactly this IP will do, same operation we will mimic in our verification environment. Otherwise, we can't compare the what exactly design is doing, right? So we will mimic the how IP will do. Same thing we will mimic in our verification environment. And whenever IP is producing the data, that data we can create in our VIP and try to compare. If comparison is matches, then design is working as expected. If comparison is not matches, there are two things. One, you have to cross check how whether IP is producing proper data or not. And another thing is your VIP is producing the proper data or not. Your VIP is working or be verifying properly or not. Okay, there are two different things. One is design. This is IP, come from the design. I forgot to mention design here. These VIPs are completely belongs to the verification only. Okay, IPs are completely belongs to the design. Okay. Okay, mostly these protocols they will use to transmit the data, receive the data, communicate the data, route the data. All these things they'll use in the design. Suppose they are having a SPI on the chip. Okay, SPI is the IP there. Okay, so how SPI will work? We will have SPI VIP and we can verify SPI, how SPI is working. Okay. So I'm suggesting go by the AMBA things here, whatever the starts with A, APB, AHB, AXI. Okay, these three are called as a AMBA protocols. Okay, nowadays they are extremely using the AXI. Okay, so AXI specs are available over the internet. You can go by it once how AXI is behaving and try to verify the AXI. If I use AXI, how data will be interchanged, that we can verify in our VIP. And AXI VIP is also available over the internet. So you can check how AXI design will be there, how AXI VIP will be there. Okay. And one more point I want to make here. Suppose on our SOC, see, you have seen SOC here, right? Here SPI is there. Okay, and most of the designers are actually designs are two types. One is they can design their own SPI, means they don't avoid the SPI rules and regulations, but they can embedded their SPI into their design, their own design according to their application. And another kind of use case design is they'll purchase the SPI and they'll try to integrate here. That's a third party IP. They'll purchase from there and they'll integrate here. For that, they spend a lot of money and they insert. So here verification is of again two aspects. One is it really necessary to purchase the third party VIP? It depends on the designer interest. If designer wants to verify how this SPI is working on this SOC, we will verify this on the system level. Means sorry, not system level, SOC level. If they have their own SPI design, we can verify it on the both level, IP level and subsystem, means top level. Okay, did you get my point? How two aspects in the design, how two aspects in the verification? They may have their own SPI design, so that we can verify that and how it will work on the top level, means with other systems how it can communicate, how it is communicating. Other thing is how can I integrate, means they'll purchase outside and they'll try to they'll purchase, just wait, they'll purchase outside and they'll try to integrate here, because when they are purchasing, whoever the design that third party guy, they'll verify how it behaves in the IP level, how it behaves in the top level. We don't need to verify here, but here it is better to verify on the top level, because it is third party, right? How it can communicate with our subsystem, it is necessary to be see. Okay, so here you have to go by all these peripheral protocols. Okay, means low speed and high speed. Okay, SPI, I2C, UART, Ethernet. Okay, USB. All these things you can understand the design and you can understand the VIP. If you want to come to a verification side, you better understand the VIP also. Okay, but it is mandatory to understand how it is produce the data, how it is consume the data, all these things on a designer level. No need to be deep design. I'll tell you how a verification can be done without understanding the design. Okay, these are the protocols. Okay, now why system Verilog? because it is coming with a wider range. Okay, it is having a multi-dimensional arrays which are not having in the Verilog. Oops, which is not there in the Verilog. Randomization, which is not there in the Verilog. Functional coverage, which is not there in the Verilog. Assertions, which is not there in the Verilog. Interface, which is not there in the Verilog. Okay, so this much development they have done from the Verilog to system Verilog. Okay, but the thing we need to understand, all these things, not at all, not all things. Some of these things are not at all useful in the design. Okay, if you see oops are not at all required for the design. Randomization. Suppose they want extreme random data in their design. They want to design random number kind of generator in their design. This can be helpful, but this is mostly slide to the verification. Okay, this coverage is mostly slide to completely slide to verification, and some of the verification kind of a simple, they'll develop a kind of a module. Those are entities which are behaves like a continuous checkers on their design, so that some of the some level we can use assertions in the design. Okay, that is lighter slide these assertions in the design. When it comes to multi-dimensional arrays, if they want to design a memory, they will go by these things. Otherwise, they won't use these things. Okay, and most of the dimensions are dimensional arrays we can use in the verification. Okay, and what is this interface? Okay, interface I'll take a little later. Okay, so if anybody is having a basic kind of a means, I want to know the lighter things about a particular things in this, you can ask me a doubt here. I'll pause sometime. I'll allow you to ask one doubt here. If you have any doubts, you can ask here.
I think we can proceed, sir.
Yeah, sure. Okay. These are the differences between those versions. Okay. You can see here. And one thing here I want to mention is this system Verilog is like it's a kind of a parallel processing language. Okay, so multiple things we can work on parallelly. Okay, that is the greatest advantage the system Verilog is having. Means I can pump the data, I can give the inputs to the data in a various parallel various levels in a parallel manner, so that design can be design can be struggled a lot to produce the output. So that much tight, that much design can be that much tight. Okay, so sometimes design will try to produce the data because of these parallel threads. Okay, so did I mention that? Okay, so there is a thing called just wait, see here, only this one. See, this is the are you able to see my screen?
Yes, sir. Yes, sir. Standards.
Yeah, see, standards, correct. This is the IEEE standards for the system Verilog. They released this recently, 1800 2023. Okay, so it is having all these things. Okay, whatever the things I mentioned there. So after this session, I'll provide this this version. If it is available for you in your institute, you can download it from the IEEE. So otherwise, I'll provide this. Okay. So if you want to learn system Verilog on your own, you can go by this. Okay, that is very standard one. If you try to depend on other websites, all came from this only. Okay, mostly in industry, people will depend on this only. Okay. No. So I told you right previously how to verify a design without understanding the design. Right? It is not necessary every time. It is not necessary to be understand the design. Okay, that's how that will make the difference between verification engineer and design engineer. If verification engineer is try to understand the design, this guy can be a designer at any time, right? So it's two different things, and I told different things, but those are hand to hand. So this is a black box verification, means you don't have any knowledge on the design, but they'll give you the pin level signals. Okay, there is a pin, right? Suppose if you see microprocessor at 086, it is having a 40 pins. What are the outer pins? Their functionality and their name they'll give. Inside how those are connected, they won't give. So then what you will do? You will develop an environment and produce the input data, and you will put that input data on those input pins, and you will take the data. Okay, and you will try to understand the output according to their specification. They'll give you the specification document, what output it will produce for a particular input. Like that, they'll give the combination, so that based on those combinations, you will write the comparison logics in your environment. When it comes to this is a gray level. They'll allow you to see some of the modules in the design, so that you can, means they have their own IP. Let's say they are not see, their application is not depending on the existing IPs in the industry like SPI or some other. They wants to design their own IP, or else they, according to their application, they wants to design their own NOC, so that they'll provide some of access to the some of the module, and you can understand how the module was written, and you try to mimic that kind of a nature in your environment. Okay, and that too they'll access very few. And here it is a white box, so they'll provide complete access to your hand, so that you can understand the complete design and you can verify in a larger level. Okay, but in all the three cases, the verification has to be effective only, whether they'll allow you to access the design or not. Okay. See, these are the various VIPs we can develop. For a CPU subsystem, we will have our own VIP. How CPU subsystem will behave? Okay, how these SPI or I2Cs are behave. Each module, each IP has its own VIP. So that if you see here, I told you already. For high speed peripheral verification, there is a one team. Okay, they have their own VIPs. That is IP level verification. Okay, you are going to verify that particular Ethernet using that VIP. So VIPs contains what? How Ethernet behaves. Almost similar mimic producing the output in the VIP. That kind of portion we will write in the VIP. So see how many VIPs are there. This is IP level, right? So in the IP level, we are verifying these guys, individual guys. When the block level, we are verifying the NOC only. Means this is top level. Means how these peripherals can communicate with this CPU, and how CPU will communicate with high speed. That interconnect only we will verify. Okay. And nowadays they are verifying the NOC as IP. That is what recent change they took in the industry. NOC, they are verifying the NOC itself. Means because previously one particular kind of NOC will be there. According to that NOC, they will connect their IPs and they'll design the SOC. Now they are interested to design their own NOC. They are not depending on the existing NOC. Okay. So for example, if you want me to tell specific thing, when it comes to my last project, they have their own cache. Okay, actually they'll follow the lighter rules of the existing cache and they design their own cache. Okay, now the things will be different, right? Existing cache verification is different, their own design cache is different, verification is different. That's it. So this is the thing, IP level verification and SOC level verification. I think I discussed mostly, but the toughest part is each has its own difficulty, but some places they are called IP as a block also, SOC as system level verification also. It depends how they'll call. Okay. See here, when it comes to IP level, it's completely depending on your system verilog and UVM. You develop your own verification environments. Okay, and you can develop your own VIPs. They'll mimic the design and later you will compare the things. But when it comes to SOC level, there is a requirement of C kind of things, because on the SOC level, processor will be the main thing, right? Processor will go and write everybody, so that processor will do things in the assembly level language, so that we need a C language requirement. Okay, so when you want to be part of SOC, you need to know a little C based, okay, C kind of thing. So I told you right previously how a verification plan will be. Okay, again we came back to the point. Suppose if you see a Ethernet, okay, what Ethernet will do? Ethernet will transmit the data and Ethernet will take the data, right? Whenever it is transmitting the data, it will behave like a master. Whenever it is taking the data, it will behave like a subordinate. Okay, don't use a word called slave, subordinate. So here, what to verify? Okay, so you have a list here. By seeing list, you will simply understand. Ethernet will prepare the packet and it will send. Okay, how it is sending? In a off duplex mode it is sending, or full duplex mode it is sending, that we will verify. Okay, means how Ethernet is having a some list of registers, which are around 21 registers will be there, and they have a one control thing. You guys all know, right, what is control thing? It's a state machine. So now what I'll do is, in my verification environment, I'll try to write one value into the register. Okay, that's called register configuration. Okay, based on that value, the state machine, based on that value into the register, the state machine will move. Okay, so try to be imagine the thing. They have a list of registers. I will try to the value to the register. Okay, now I'll come to a point like what value I need to be write into the register. They'll give you the list. Okay, if you write this value into the register, this will happen. If you suppose they're having a mode register. Okay, that mode register, if I write, suppose I'm telling an example basis, if I write a value to the mode is 200, then it will behave like a off duplex. Means in the state machine, off duplex mode will be enabled, so that your entire Ethernet will behave in the mode of off duplex. So now what I'll do is, from my verification environment, I will prepare the data 200 and I'll put in the register mode register. So now I will understand, so whatever the data coming from the Ethernet as a transmitter, is it proper or not? It is according to off duplex mode or not? Okay, that logic I'll put in my verification environment. Whatever the data coming from the Ethernet, my verification logic will generate one data and these two will be compared. So if those are matches, now Ethernet is behaving properly and it is behaving in the off duplex mode. Okay, like that, so many things are there. Suppose I want to configure my Ethernet as unicast, means one Ethernet can communicate with another Ethernet. Okay, So for that there is a register. Okay, I will put one data into the register, then Ethernet will behave like a unicast or not, then I'll see that. Okay. So different different types of packets. Small packet will be there, the size of the packet, normal packet, large packet. Okay, I will prepare one packet. Okay, Ethernet design will prepare one packet. Both I'll compare. Okay, so that is one more thing. Like that, based on the designer given specification document, I'll prepare this plan. Okay, nowadays most of the designs are coming with a register based, means they have set of registers and they have one state machine. So behind logic is different, that is data flow. If I write something into register, this register connected to the control flow, means state machine. State machine will change according to register value and enable the data flow logic. Okay, so nowadays most of the designs are like this, because this is the comfortable way of doing things and it is effective also. Okay, suppose I enabled the off duplex. Okay, it will send data. Meanwhile, on the same line, one more data is coming. Those has to be collision, right? So in order to collision is happening or not, how collision is happening, those plan we will verify. Suppose if I configure as a full duplex, for a transmission one line, receiving one line, there is no possibility of collision, right? So I'll check how transmission is happening. I'll check how receiver line is happening. I'll try to control the transmit line, means I can pause the transmitting data, I can pause the receiving data, all those flow controls I'll verify. For all those things, I'll write the items. Those are verification items. Based on that, I'll write my test case, right? See, at the end, you have to understand it like there will be a one environment. Test cases will be different. Okay, we don't have a separate environment for each test case. Here I wrote total 11. In each 2, 2, 3, 3 are there. So those many environments we don't develop. One environment, each item is one test case. Okay. So for you to understand the thing, see here we will plan it and we will develop it and we will pump the data into design and we will check whether the coming data is correct or not. Okay, at the end we will do the coverage analysis. Okay, so here this is your verification part, this is your design part. Okay, so test bench, from test bench test case will go. Okay, this is the okay, I'll show you the environment, then you will understand. See, this is the thing. This is the very initial part. Okay, from the test bench, stimulus means whatever the input data you are putting. Okay, in the test bench you will generate the stimulus, means input data that will go to a design. Design will produce the output that will monitor. Okay, we will cross check whether the data which is coming from the design is correct or wrong. This is the initial test bench. Okay, now they changed. They have a separate test bench and there is a DUT. There is a connection between them is interface. Okay, this interface is having all the pin level signals, means I told you, right, 8086 is having 40 pins. Those 40 pins they'll put in the interface. They will use this interface in this test bench. They'll generate the data. Again, they'll give it back to interface. Interface will put that data in the DUT. Okay, if you see here, see, this is the current situation. Okay, in the test there is a environment. In the environment there is an agent. In the agent there are three things like sequencer, driver, monitor. All these are classes. I want you to understand. Okay, we have a OOPS concept, right? All these OOPS can be are classes only, not the modules. You have to understand. Here the only module is top TB. So this test will put in the module. Okay, we didn't put this test in the class, we will put in the module. Okay, All these guys will generate the data and they'll give it to the interface. Interface will put the data into DUT. DUT will produce the output. That output can be compared in this place. Okay, the place called scoreboard. Okay. So this is another showing. See here, this top will be the module. Okay, in this top test will be there. In this top test will be there. Test is a class. In this class, one more class which is environment. In this two classes, more than two classes will be there. Like agent class will be there. Class name is agent. Okay, this scoreboard is a class. This is one more class, like that. Okay, these classes will generate the data and they'll put the data into the DUT through interface. Okay. Yes. Now, what is the main purpose of this test bench? Okay, we can reuse this test bench in a different manner. Suppose if you try to develop one particular environment, it can be useful for many designs, not for only one particular design. Okay, because what is the biggest change we need to do? We need to do a change in the signal level only, right? There is no change in the environment. The environment is fixed. Like in the top, test will be there. In the test, environment will be there. In the environment, agent will be there. In the agent, other things are. This is fixed. The only change is signals. Okay, we will change the signals and we will generate the some values to those signals in the environment and we will send the data to design. Okay, environment won't change, so we can reuse this environment for any kind of a design. Okay, only signals level will change. Okay, now modularity means you can modulate this to different aspects, right? If you want if you don't want a one particular class, you can remove. Just by disabling it, you can remove it. Scalability means you can scale this environment to any level by using a multi-dimensional arrays. Okay, you can create 100 environments for one design. Okay, 100 environments in parallel, they'll put the data. Now we will understand how design is behaving. Okay, and we will configure those 100 environments. Which environment has to give the data, which environment has not should not give the data. So like that we will configurable. Okay, interoperability means in 100 environments can talk each other. Okay, let's talk, let's do like this. Let's send the data like this. Okay, let's take the output like this, so that they can talk each other. Like that we can connect them. Okay, controllability, we can control extraordinarily. Like I want these many environments has to send this data. I want these many environments has to send this data. Based on using a configurable, we can control those guys. Okay, and we can extremely observable those things. Means which environment is sending which data. Means which test bench is sending which data to the design. Okay, so that is observability, right? So at the end, one thing you have to understand, like a design has to be controllable and observable, right? We can't create infinite things, right? We can't create a things like we can't use a things like which are not under control. Okay, not under observable. So whether it comes to the aspect of verification, whether it comes to aspect of design, both has to be controllable and observable. Okay, and remaining things will come later, like a reusability, modularity, those things, right? All these guys are classes except that top is a module. Okay, everybody whoever you are seeing there, controller, coverage, monitor, scoreboard, driver, generator, all these guys are classes except that DUT. Okay, and all these classes are can be these guys, can be reusable, can be modularable, can be scalable, like that. Okay, so analog mixed signal verification, like you see here, you can generate, you can do analog things in the MATLAB. There, from there you can give it to the C. That C code we can use in the environment. okay, using a DPS called direct programming interface, right? So whatever the analog things you want to do, you do all those things in the MATLAB. Okay, MATLAB will convert that MATLAB code to C language, right? That C language I can use in the environment. Okay, that facility also will be there. So that's how we will do the analog mixed signal, means analog and digital things. So at the end, I'll tell you one. The next thing. Okay. See here, there are various things like whatever the items you wrote in the verification plan, all are verified or not. That is one point. Another point is whenever you are randomizing the data and putting in the design, complete code is covering or not. Suppose there is there is a mux. Okay, 2x1 mux, let's say. It is having a one selection line, two inputs and one output. So every time whenever you are randomizing the data, okay, the data is coming to the design. In the design, the selection line is becoming always 0. Means what? If you see a mux, simple mux, which is having a 2 combinations, every time whatever the data I'm putting into the design from my verification environment, it is always 0. Means one of the condition of that mux is not verifying. So what is the coverage percentage of the mux? Can anybody? Every time putting 0 only. So when mux will be verified, if selection line is 0, we will check output is equal to 0th input. If I put selection line as 1, we can understand the output is first output or not. So that every time if I am putting 0, only one portion of the mux is verified, right? That is 50%. So all those things we will verify in the here in the code coverage. Okay, in your plan items, if you verify all those things, your test coverage is 100%. Next, we will see the how much design code is covering with your random data. Okay, like that many things are there. So like we will generate the random data. How much random data you are generating? Okay, for example, there is a see just now there is a state machine. Okay, it is having a let's say 20 states. Out of those 20 states, if I'm generating one random data, only 10 states are moving. Okay, our data is not making that state machine to generate the remaining states. So then what is the coverage of the state machine? It is again 50 only. Again 50 only, because out of 20 states, I'm moving that state machine to 10 states only, so that I'm not generating the random data effectively. So that I has to generate and I make the state machine to run to change 20 states. Okay, like that we will cross verify everything, then we can tell it like verification is done. Okay, there is a state machine, you are not verifying some of the states. How can you say that verification is done, right? Suppose in one of the state, whatever the states you are not verified, in that states, if any bug is there, let's say in that state there is a design, some design will be there. If any bug is there, so we are not going to find that bug, right? So that's it. Like that we will generate the data and we'll understand what and all the covered. Okay, entire design code is covered or not. Okay, entire design function is covered or not, like that. So these are the other ways of verification. We have a FPGA verification also, and we have a formal verification, completely mathematical based verification is there. Okay, and just by writing the conditions, okay, if some signal is like this, what will be the other signals behavior? Like based on that, we can simply verify the design. That is assertion based verification. Okay, by generating the huge random data, we can verify. That is constraint based verification. By seeing the how much code is covered, that is coverage based verification. Okay, analog and mixed signal verification, like that many more are there. So this is a simple scenario of the verification. So there are 21 masters are there, means 21 IPs are there. This said 24 IPs are there. All are connected with this chip. Okay, this is my previous project. Okay, now here I verified how this knock is doing things properly or not. So can somebody please tell me what are the various things I can cross check on the chip? Any idea? Here in this example, what and all various things I can cross check, I can verify. Can anybody? Anybody wants to put any point here? I'll repeat my question again, my point again. There are 21 IPs this side. There are 24 IPs this side. Okay, all has to communicate with each other. So what are the various things we can encounter here? In the real time, there will be on the chip, there will be a big memory, right? In that memory, all these 24 IPs, all these 21 IPs are mapped in a particular address range. Means all are register based, right? Register having a certain length, 32-bit. So that in the memory, some particular range give it to the S1, some particular range will give it to the S2. Now, suppose M2 is putting data to S3, where S3 will be there in some address range. Okay, NOC should have that intelligence. M2 is putting one data to S3, it has to go to S3. Suppose it is going to some other some other subordinate, then what is the situation? That is wrong, right? So whoever I want to give, they has to take. If somebody will take, they may misuse or they may not use, they may throw it, okay, they may manipulate it. Many things will be there, right? And that is one point. Another point, whenever M2 is putting the data to S3, S3 has to give the response, right? Yes, I took the data, it is done. So M2 has to understand S3 sent the response. So that
Acknowledgement.
Acknowledgement, exactly. That acknowledgement also network on the chip has to give M2, right? Suppose I'm giving to somebody, okay, they whoever I'm giving, they took, but they are giving acknowledgement to somebody. So that is not proper way of doing things, right? So what the thing you want to understand here is, most of the designs are request and response based. Okay, first they'll put request, yes, I want data. Okay, for that request, suppose M2 wants to put some request to S3. Okay, I want some data from you. For that request, S3 has to give response. Okay, once response came, must give the data. Okay, like that, there are layer by layer things will be there. Okay, so whenever S3 took the data, it has to give the response. That response has to take by M2. Okay, all these routing things has to be verified by the NOC. Okay, next. See, we have a 4 MB memory. In that 4 MB memory, I can give the address range, memory range to S1, S2, S3 till S4, S24. So I assigned memory S1 to S24. Still I have a 1 MB memory space. Okay, that is not assigned region, right? And did you get my point? So how this assignment will be done? There is a decoder in the design. That decoder will tell this has to go this side, this has to go this side, this has to go this side. Now when it comes to unmapped region, 1 MB is remind, right? Suppose M2 is putting the data to that unmapped region. Okay, so network on the chip has to take the responsibility to tell, like, there is no particular design or IP in that region, so it cannot be reached there, it can be bounced back. That is one point. See, another thing, there are 3 things: deadlock, live lock, starvation. Okay, you can create a scenario like here, M2 wants to communicate with S3. Okay, all of a sudden M19 wants to communicate with S3. Now things will be different here. if you understand in a one particular way, it will be like one thing. If you understand in another particular way, it will be like another. Means M2 wants to put data to S3. M19 wants to put data to S3. Now network on chip NOC has to be NOC has an intelligence to which master I should serve first based on the priority. Okay. Suppose M19 is having highest priority. Now M2 data is not reaching S3, right? So M2 is under low priority. So their data is not reached to the destination. That is what starvation. Okay. Their data packets are dropped on the NOC only. Okay. Next, live log. If I want to put data from the M2, data is not going anywhere. It is roaming all or around the NOC. It is in the NOC, it is going to some other direction. From there, it will going to some other direction. That is live log. Okay. Then what is dead log? If it will go to a different thing, it has to go to normal S3, but it is going to some other guy. Okay. That guy is giving response. Okay. M2 is looking for S3 response. So M2 never get a response from S3. So that's what there it's locked like all responses are on the NOC and on the NOC only. They don't go to the source and destination. That's how deadlock. All these things we verified in our thing, right? So they designed their own NOC. Next. And we designed a memory also. We verified the memory also. Memory is having a cache memory. So from for one address location, if all masters want to access, okay, then what will happen? All wants to, these M1 to M21 masters IPs wants to access from one location. Okay, let's say 4th 192 KB. From that, it wants the data. Then what NOC has to do? NOC has to check the priorities of the masters. Based on that priority, NOC has to put the things in a queue. Then serve one by one. Okay, whoever it is serving, it will take the responses and give it back to all the masters. It has to give the respective master. Okay, that intelligent NOC should have. Okay, that is called a back pressure. Means not one to one, many to one. Then many things will come into place. Then how NOC is behaving. Like that, we will send a 21 masters data at a time. Okay. Now coming to our verification environment. This memory we will take from the design. All these masters are VIPs. I'll put my VIP 21 times. Each VIP will send the data. In the real time, 21 IPs will be there. 21 will give the data. Same data our VIP will give now. Now, how they are going to the memory, from memory, how they are coming back, all these things will be verified here. So you know all anything about SPI. It is like one master, many subordinate. Okay, master will be one, subordinates will be many. It is just a data exchange like this. Here one register will be there. It will send 8 bits, 1 bit by 1 bit. And this register Y also can send the data from that side to this side. Okay, one bit can be go at a time. Okay. And there are other things also. DSPI, QSPI means four bits can go at a time, two bits can go at a time. Okay. So like this. So SPI, this is the master. Master wants to give the data to all the 3 subordinates in a different fashions. Okay. At a time it can give. See here subordinate pins are 3. So that I can connect 3 pins. I can start giving the data to 3 at a time. Suppose there is only 1 pin, but our subordinates are 3. Then how we will connect? Suppose from master to subordinate 3 it should get. Then it will give to the S1. From there it will give to S2. From there it will give to S3. That is called daisy chain. See, this is here. There is only 1 pin here. So that will give the data to this. This guy don't consume data. It will just throw the data to this from here to here. Okay. Different things are there. See, I told you as previous, all are register based only. Master side is having some registers, subordinate side is having some registers, and they'll put the data into those registers. Okay, here I kept 8 bits. after 8 clock cycles, I got the data. Okay. So these two will go after 8 clock cycles. Okay. These are the various registers which are inside the SPI. So I want you to understand there are registers, there is a control mission, and there is a data flow. That is the current design trend. Okay. Those things we don't need to put on in environment. They'll give you what data I has to write into the register. Data is generate and write. Design will go output. I'll compare an output in the environment. Okay. The various things we can compare with each other. Okay. This is how verification. When it comes to the testing, it's a different story. Okay. Mostly this is a physical testing. Okay. So circuit under test. Okay. We will generate some test pattern. See, on the chip level only they'll verify those chips are having a defect or not. I'm talking about physical thing, not a yes or no. So here they'll put the data on the chip only. There is a DSP processor. Processor is having some port level chips, right? Port level pins, right? On those physical pins, they'll put the data. Okay, that data is going inside and coming outside properly or not. That pin is taking the input or not. Like that, they'll put the bit pattern. Okay, so that they'll understand. Okay, pins are working properly or not. Okay, that is one thing. Another one is any faults are there, any defect are there, any error are there, any failure are there. They looks very similar, but there's completely different. Okay, defect is different than what is that? Defect is different than fault. Fault is different than error. So that here the major protocol is JTAG, Joint Text Action Group. Okay, there is a ATPG also. This Joint Text Action Group put the bits, put the test pattern on the pin level using a ATPG. ATPG is nothing but a automatic test pattern generator. It will generate the pattern that will put it on the level. So I know this much about testing because I'm not a testing guy. So that is the point. Okay. So now you can ask any questions you have. Oh, if anybody is having any questions on a verification side, you can ask, you can shoot your questions.
There is a question in chat box, sir.
Yeah, you asked. I'm sorry.
Which interface is best for sharing the data to test?
Which interface means it is not like that, sir. We will see interface is like an entity, like how our module and module is there. Like that, interface will be like interface and interface. We will keep all the design signals in the interface. We will take all the signals from the design and we will write in the interface. Those signals will be generated in the verification and give it to the interface. Interface will pump the data into design. So there is no specific kind of interface. Okay, we are having only one kind of interface, like interface and interface. We'll put all the signals. You got that point? Whatever I'm telling.
Yes, sir. Yes, sir.
Yeah, there is nothing like a specific interface to specific design. So there is only one entity called interface and interface. We have entities like and module, class and class, interface and interface, program and program. All these things will come in the environment verification side. We'll put the signals here and we will pump the data. Any other question?
Okay, sir.
If you want me to show, I will show you very quickly so that you will understand how the interface will be. Then your
Yes, sir. Yes, sir. Please,
confusion
sir.
I got into. Yeah.
Please, sir. Please, sir. Yes, sir.
Just a minute, I'll show you. See here, SPI. See sir, here we are having an environment. This is our interface. Like this, sir. This is interface and interface. So we will put all the signals on the in the interface only. Okay. These interface are available in our verification environment like this. So this is our VA interface, sir. SPI interface. Are you able to see my screen? See, sir. Here I am putting my own data on the interface. Yes, sir. This interface will go as a this interface will pump the data into the DUT like this, sir. See here. See, I connected my interface signals to the design. That this DUT1 is the design. Okay, here my interface is there. I'll connect my interface to the design signal. Now I will generate the data in the interface and I'll put the data in the interface. This interface will give it to the DUT based on this connection. Okay, we can do the dot convention or we can connect like this also. Now I hope you got the point, how those are connected each other.
Yes, sir. Yes, sir.
Yeah. Still you have confusion, still you wants to know more things. You will take my contact from Vasu sir and you can ask me. I'll tell you. Anybody is having any other question? If the project level is entirely different, sir. Whatever we are designing in our academic level, it's a very lightweighted module. But when it comes to the industry, these are like 100 crore, 80 crore, 120 crore level modules, cost modules. So the verification is also that much level.
Sir, good evening, sir. Actually,
Yeah,
your
good
insights are very nice.
Yes,
And
sir.
also, we got many things as well as you are experienced. Also, you
Yes.
shared to us. But I have a small doubt, sir.
Yes. Yes.
Actually, as you said, okay, the test bench
Yes.
is bidirected to device under test, I think.
Yes, sir.
Yeah, test bench. Intermediately, you can given the flow bidirectional flow.
Yes, sir.
So, why should we use bidirectional flow for between this, sir? Actually, once we complete the test bench, then only that is given to the device under test.
Yes.
Yes, sir. It's
Yes.
a unidirectional only, but you mentioned in a bidirectional way.
Can you please tell me where exactly I mentioned it like a bidirectional way? From the design to the test bench, that's what.
Yes, sir. Test bench to DUT, device
Yes.
under test.
Yes.
Normally,
Yes.
what we'll do first, we have to initially we done the coding.
Yes,
Then
sir.
after that we can do the simulated. Then we
Yes.
can do the test bench. Then after test bench only we go for the further fabrication, all the things and all.
Yes. Yes. Yes.
But you mentioned it's a bidirectional flow, so that which indicates that bidirectional. Whether it's any error also we can go back to. That is the intention you mentioned.
Yes, sir. Suppose that the main aspect of this test bench is to verify all the combinations, all the functionality of the design, right?
Yes,
So
sir.
that
Yes,
I
sir.
has to take the data from the design, whatever the design is producing, that will come back to the verification environment. In our verification environment, we will generate that data and we will try to compare with the design data. So that is why it needs to be bidirectional, like verification will put the data, design will give the data, and we will compare here. So then only, right, we will understand that function is fulfilled or not in the design.
And also one more doubt, sir.
Yes.
I think you have shown so many results. What software you used for this?
We are having a tools like a Cadence tool, Synopsys tool, Mentor Graphics means Questasim. Those are Cadence and Synopsys are very.
These are open source or licensed?
No, sir. Per month they took 6 lakh Cadence tool.
Okay.
Oh,
Then
yes.
Mentor Graphics.
Mentor Graphics Questasim is available, sir. Cracked version is available over the internet. You can try those things in the Questasim.
Okay, okay.
So
Thank you,
when
sir.
you are trying, if you stuck anywhere or if you want me
yes,
to
sir. So that
lighter note,
you
you
just share
contact
your
me, sir.
yes, sir. Share your contact number as well as mail ID.
Yes, sir.
And also try to download open source and keep on working. Is there any doubt and clarifications? We will contact you, sir.
All the time, sir. All the time. You can ask me 24/7 at any time. I will be available.
Okay. Thank you for your kind information as well as your given lot of information. That is also we try to implement in our future, sir. Thank you.
Yes, sir. Thank you. If you have any other questions, anybody, you can ask. Vasu, sir, can I keep my contact here or you will give?
Okay, sir. I will give, sir.
Thank you.
Okay. The session on VLSI design verification and testing delivered by Mr. Naga Subramanyam was an invaluable contribution to the 6 days ATAL faculty development program on VLSI design innovation for defense application. He detailed insights into critical aspects such as VLSI design, verification methodology, advanced tools, and scripting languages provided immense value to all participants. On behalf of the organizing team, we extend our heartfelt gratitude to Mr. Nagasubramanyam for sharing his valuable time and knowledge. His efforts have significantly enhanced the program's impact, and we look forward to future opportunities for collaboration and knowledge sharing. In conclusion, this session has been a remarkable addition to the program, inspiring participants to develop deeper into VLSA design and verification. Thank you once again for your enlightening presentation and contribution to the program's successful. Thank you so much, sir. Thank you.
Thank you.
Thank you, sir. Thank you.
Yeah.
Sir, thank you, sir. You kindly share your mail ID, sir.
Yeah, sure, sir.
Okay, sir.
Yeah.
Bye, sir.
Thank you. Bye. Bye.
So feedback link is shared in the chat box. So please, dear all the participants, please fill the feedback. And it is also given in the WhatsApp link.
Ma'am, if it possible, you have to share that mail ID of
Also, sir, it is given in the WhatsApp.
WhatsApp. Okay. So both the sessions you got to share, ma'am. Both the experts.
Okay, sir.
Thank you.
Thank you all.